In Lesson 3, we'll see how functions work with near numbers. For anyone that wants a brief review of functions and graphs, there's a short prelude video to view first. A link is provided in this video's description. We'll pick up right where that left off, with the reciprocation function mapping x to 1 over x. We use graphs with near numbers via exactly the same input to graph to output process as we did with numbers. The only difference is that our near numbers squeeze. What happens if we put the near number 1 plus into this function? In other words, what is the reciprocal of 1 plus? We put 1 plus on the input axis, push all of those points up to the graph, and push them over to the output axis. Of course, 1 plus squeezes and the rest follows along. What do we see on the output axis if we turn our heads to the left? The result fits our model of 1 minus. If you understand that one example, you get the basic idea of this video. This process works in the same way for any function and for any near number. The rest of this video will just work through some important examples to illustrate the process and present a few more details along the way. A quick remark before we keep going. Let's look at that last example again. Our result doesn't just fit into 1 minus, it's actually equivalent to 1 minus. If we wanted to, we could use a double-headed arrow here, and in every other example we'll see during this video as well. But we'll just write fits into to get ourselves into the right mindset. Now what about the reciprocal of positive infinity? We just put positive infinity on the input axis, push up and over, squeeze, and watch. Let's zoom in to see this continue. The result we see is 0 plus. So 1 over positive infinity fits into 0 plus. The reciprocal of positive infinity is 0 plus. What happens if we reciprocate again? We put 0 plus on the input axis, push up and over, squeeze and watch. Let's again zoom in to see this continue. Our result shows us we have positive infinity back again, so positive infinity and 0 plus are reciprocal to one another. In the same way, 0 minus and negative infinity are reciprocal to each other, and as you could guess, 0 plus minus and positive negative infinity are reciprocal to one another. We've seen how to reciprocate 3 different near numbers squeezing towards 0. 0 plus, 0 minus, and 0 plus minus. What about the reciprocal of 0 itself, that is 0 dot? Working from the graph, we put 0 dot on the input axis, and we push up and over, but nothing's there. We don't see any output points at all, so it looks like the result should be the empty set. But we've lost something here, namely the 0 that we put into our function which wasn't in the domain. We note this with an asterisk on our result, indicating that undefined results were encountered. Once we have this asterisk, no matter what we do with this near number, the asterisk will stay, marking that points were lost. It's important to note that as long as we don't feed numbers to a function that are outside its domain, and we really shouldn't have occasion to, we will never need to use this asterisk. An asterisk indicates that we've applied a function wrongly. Calculus does not make functions that are undefined at some point suddenly defined there, but near numbers do allow us to precisely express a function's value nearby those points. One last example before we leave this function. What is the reciprocal of 0.1 plus minus dot? We put 0.1 plus minus dot on our input axis, push it up to the graph, and over. Yikes, this is a mess. And we've lost the input value 0 in the process. But let it squeeze. Once our input squeezes far enough, zooming in, our slice of 0.1 plus minus dot no longer contains 0, so the asterisk drops off. What we see now is simply 10 plus minus dot, which is our result. Again, we'll never see an asterisk on a result unless we've really done something that we shouldn't have with a function. Staying with powers, let's move on to the squaring function x maps to x squared. Squaring 2 minus, in, up, over, and squeeze, we see the result of 4 minus. Squaring negative 2 minus, meaning negative 2 minus, in, up, over, and squeeze, we see 4 plus. Squaring positive infinity, in, up, over, and squeeze, we see positive infinity. How about negative infinity? In, up, over, and squeeze, we see positive infinity again. No surprise, squaring positive negative infinity, in, up, over, and squeeze, we see positive infinity. Every other near number works in the same way with this function. One more power. Let's look at the square root function x mapping to the square root of x. The square root of 4 minus, in, up, over, and squeeze, we see 2 minus. The square root of 0 plus dot, in, up, over, and squeeze, we see 0 plus dot back again. 0 minus isn't a sensible thing to take the square root of in the context of real numbers, as negative numbers aren't in this function's domain. So, 0 minus, in, up, over, and squeeze, we see the empty set with an asterisk. This is something we have no reason to do in the first place. The square root of positive infinity, on the other hand, is just fine. In, up, over, and squeeze. The result squeezes more slowly, but it eventually hits any target positive infinity paints, so the square root of positive infinity fits into positive infinity. Here's a simple function, the negation function, x mapping to negative x. Negating 1 plus, in, up, over, and squeeze, we see negative 1 minus. We're not about memorizing rules here, but the rule for negation is really simple to think about since negation reflects the real line about 0. Negation negates the base of a basic near number and also negates the adornment. Negating 2 minus dot, in, up, over, and squeeze, we see negative 2 plus dot. Negating 0 plus minus, in, up, over, and squeeze, we see 0 plus minus back again. Negating positive infinity, in, up, over, squeeze, we see negative infinity. Okay, let's move on to some more interesting functions. How about the exponential function mapping x to e to the x? The exponential of 0 plus minus dot, in, up, over, and squeeze, we get 1 plus minus dot. The exponential of positive infinity, in, up, over, and squeeze, we see positive infinity. The exponential of negative infinity, in, up, over, squeeze, we see 0 plus. The exponential of plus minus infinity, in, up, over, squeeze, this one's a bit of an oddball. We could describe the result quite well, though, as the union of 0 plus coming from the negative infinity and plus infinity coming from the positive infinity. Now let's look at the natural logarithm function mapping x to ln of x. Some of these results won't be surprising given what we just saw for the exponential function. We're just pushing things back where they came from via the inverse. The natural logarithm of 1 plus minus dot, in, up, over, and squeeze, we see 0 plus minus dot. The natural logarithm of positive infinity, in, up, over, and squeeze, we see positive infinity. The result squeezes more slowly, but it eventually hits any target positive infinity paints. The natural logarithm of 0 plus, in, up, over, and squeeze, we see negative infinity. The natural logarithm of 0 is undefined, so the ln of 0 dot fits into empty set star, just as we had for the reciprocation function. And just as in that case, we should never see this come up, as we should never be taking the natural logarithm of the number 0, or of any negative number for that matter. We're not interested in putting numbers into a function that aren't in its domain, though we very well might want to squeeze toward those numbers. One last function example, the sine function. The cosine function is very similar. The sine of 0 plus minus dot, in, up, over, and squeeze, shows 0 plus minus dot. The sine of pi over 2 plus minus dot, in, up, over, and squeeze, we see 1 minus dot. Let's put positive infinity in. Push up, push over, we see the whole closed interval from -1 to 1. Now let's see what happens when we squeeze. Absolutely nothing. No matter how far positive infinity squeezes, the result is always this same closed interval. So the sine of positive infinity fits into the constant interval -1, 1. The same thing happens for negative infinity and positive negative infinity with the sine and cosine. As usual, memorizing the particular results we've seen today is not the objective. These are just guiding examples showing some important functions. The goal is to be able to think through what happens when any function operates on any near number, just as we've done here. As we mentioned earlier, all the fits into arrows we've written are actually equivalences, but we want to get used to using arrows. Now that we've discussed how functions work with near numbers, we'll next move on to arithmetic operations and expressions. Then we'll finish with formal proofs of near number statements. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.